we're looking for properties of water at specified states. And so there's part A and B, C, D, E. And so it's part A, just says here's at 290 degrees C and 2 megapascal. Okay, well, 2 megapascal you can convert, and that's 20 bar. You're looking for the internal energy, U. Well, what you can do is you need to determine if it's either a subcooled liquid or two-phase liquid vapor mixture or superheated vapor. And you look at the piece of information given, and here they give you both temperature and pressure. So what we can do is use the temperature information and get the saturation pressure given the temperature of 290, and then compare that saturation pressure with the actual pressure. Okay, so we go to table A2 and we look down until we find the temperature of 290, and then we read off that there's 74.3, let's say 74.36 bar. So this is 74.36 bar. Then we compare that saturation pressure with the actual pressure of 20 bar. So we find the actual pressure is less than the saturation pressure for our given temperature. What would we conclude? Well, it's superheated. It's at a lower pressure. It's going to be in the vapor state, superheated vapor. We can do the same thing, focusing first on the pressure. So let's take a look at table A3. We look down at pressure until we find where the 20 bar is. Okay. Then we read off the saturation temperature. So we find the saturation temperature at 20 bar comes in at 212.4 degrees C. And we compare, what is our actual temperature? 290. So our actual temperature is greater than the saturation temperature, and we conclude it's superheated. Same conclusion, superheated. Superheat is just a perspective. Are you comparing pressures or are you comparing temperatures? So compare the actual pressure with the saturation pressure given that temperature, or the actual temperature compared to the saturation temperature for that pressure. Okay, so now that we conclude that they're superheated, we go to the superheated table. So I just continue to copy over the problem statement. And we go to table A4 for superheated water vapor. And we find the pressure block of 2 megapascal, and it's nice that they remind us that, hey, at 2 megapascal is 20 bars, so it's less error prone to find the right pressure block. And this is what I mean by a block of data. All of this data is for that 2 megapascal pressure. So we have a column of temperature, specific volume, internal energy, enthalpy, and entropy. And we take a look, and we're trying to find it at 290. So we march down and we find the temperature of 290 is not a line in our table, and so we have to interpolate to find the U. What I like to do is construct a mini table, a small table. Here's temperature, and our property of interest is U, and so the data in the table, the lowest value is 280. And the higher value around our value of interest is 320. And then we read off, and we have to get this value, 2736.4. And this value, 2807.9. And the question is if I have a value of 290, what is my U? What's my interpolated U? You can go ahead and construct a little plot if that helps. Maybe you think about the temperature and internal energy values, and you're coming in with the value of T1 and U1 and T2 and U2, and then a T in between the two, and you're trying to do a straight line, come up, and then come across to get the value of U. Okay, I like to do this in two steps. I like to do the fraction in the temperature. So it's, going all the way to 290 from 280. That's the numerator, and I divide by 320 minus 280. If you think about it, it's the fraction of the distance between these two values of temperature that are bracketing. Like this is 280, this is 320, and we find that this fraction for this problem comes in at 25%. So 1/4 of the way. If you're trying to draw it, accurately, maybe I'm showing it a little closer to 1/3. So if it's going to be more like 1/4 here, 1/4 of the way between the 2 points. Okay. Now once I have that fraction, I use it to get the interpolated u. Here, maybe I'm going to say this is u at 280 plus that fraction times the u at 320 minus the internal energy at 280. Okay, let's substitute our numbers. So we have 2736.4 plus the 25% times 2807.9 minus 2736.4, and then we compute the final answer, 2754.3 kilojoules per kilogram, and box it. Okay, you're not going to probably spend this much time on an exam doing an interpolation like this. You'll do it a lot faster. But when you're brand new to it, go slow, take your time, think about what you're doing, and you'll get it down. And speed, you'll naturally increase with speed. Let's take a look at the next one. So for part B, it says, given a temperature of 200 degrees C and a pressure of 5 megapascal, find that internal energy. Well, it's the same type of process. I need to find out, is it subcooled liquid / compressed liquid, either way you call it, or is it two-phase liquid vapor, or is it superheated vapor? All right. So given a temperature or a pressure, I can look at it from the perspective of, is the actual pressure greater, equal to, or less than the saturation pressure at the 200 degrees C given? Okay, or I can take a look and say, I'm going to use that 5 megapascal and calculate the saturation temperature at 5 megapascal, and then compare that with the actual given temperature and say, is the given temperature greater, equal, or less? So it's a little awkward maybe at first when you're doing this, but it comes naturally. A lot of times I think people are a little easier at looking at temperatures, because you would typically say, oh, it's a subcooled liquid, it's a lower temperature. So maybe I should have left some room. Maybe I'll do that, get this out of the way and put this over here, and then say, okay, well, what does it mean when it's subcooled liquid? Well, the actual temperature is less than the saturation temperature at that pressure. Okay. How about two-phase? Well, the actual temperature is equal to the saturation temperature at that pressure. And in superheated, the temperature is greater than the saturation temperature at that pressure. All right, how about from the perspective of pressure? Well, here the actual pressure is greater than the saturation pressure at that temperature, or the pressure is equal to the saturation pressure at that temperature, or the pressure is less than P sat at the given temperature. So because you're given both temperature and pressure, you can do it from this perspective or that perspective, either way. So let's take a look. Here's the problem repeated. We'll go to table A2. Here's our 200 degrees, and we come in with a saturation pressure of 15 bar. Well, how many megapascal is that? Well, it's 1.5 megapascal. So we're at, the actual pressure of 5 megapascal is greater than the saturation pressure of 1.5 megapascal. So Psat, and this is greater, and then so P is greater than Psat, you conclude it's compressed liquid. Okay, so we say it's compressed liquid. If you go to table A3, you look at the 50 bar, 50 bar, and then we find this temperature 264, and then we find that that temperature Tsat is, the actual temperature is lower, so maybe I try and write it up here. The temperature is lower than the saturation temperature at that pressure. Again, the numbers 264 is greater than the 200, hence we would conclude that this is subcooled liquid. Same, subcooled liquid, compressed liquid, either way, it's in the, it's not close to saturated liquid, it's compressed liquid. Okay, so we'll go to our table A5, and here it's compressed liquid water table, and we look for our pressure block of 5 megapascal. Here's the pressure block of 2.5. Here's our pressure block of 5 megapascal, and we're looking for a line of 200. So to economize, they didn't repeat the temperature column over here. Maybe they should have. Maybe it'd be a little easier, but you find the 200, and then you just have to read all the way across. Okay, when you read all the way across, you're looking for the internal energy at 5 megapascal, 200 degrees C. You just read it off. It's 848.1. 848.1. So there you go. No interpolation needed. Just reading directly from the table. Okay, another problem. Part C. So we have 2 megapascal and now a specific volume. Well, here you're only given this pressure, so you only use like table A3, which is the pressure table for two-phase liquid vapor water. And what we want to do is we want to come in and compare. We'll get out of that table V sub G, and then we'll get out of that table V sub F. And then we ask, is our given V less than V sub F? Well, if it is, then it's compressed liquid. Is it in between? Our given V in between the two values of V sub F and V sub G. Again, this is saturated liquid, and this is saturated vapor. Okay, then it would be two-phase, and if V sub G, if V was greater than V sub G, it's superheated. So two-phase, superheated, and here it's going to be really hard to have it much less than that, but it will call it compressed liquid. Okay, so let's go to our tables. We'll go to table A3 because it has the pressure as the input and the first column. We look down at 20 megapascal, which is 20 bar, and we're looking for V sub F. Here's our V sub F, so 0.00116767 meter cubed per kilogram. That's our V sub F, saturated liquid, specific volume. And then V sub G is 0.09963 meter cubed per kilogram. And then we say, is our given value of 0.0595 in between? And it is. Hence, we conclude that it's two-phase. And so to calculate the enthalpy, we first calculate the quality X as a function of our specific volumes. So our given V minus the saturated liquid at that pressure divided by V sub G, saturated vapor at that pressure, minus V sub F, saturated liquid at that pressure. So let me just put our numbers in here. Our given V 0.0595, subtract 0.001167, 0.09963 minus 0.001167. When you run this, you should get a number that's between 0 and 1. In this case, it's 0.5924. Save all the digits in your calculator. It's between 0 and 1, so that's good. Now let's use it to calculate our H. So our H is going to be H of F, our saturated liquid enthalpy, plus the quality that we just calculated times H of G, or saturated vapor quality, minus H of F. Now, enthalpy, we often have to take the difference between H of G and H of F, and so they added one extra column for enthalpy. It's the evaporation enthalpy. It's the difference. So this H of G is the difference between H of G minus H of F. They could have put SFG in, and I've seen that in other books, and very rarely would they put UFG, but they could, or VFG. I've never seen that in any book, but sometimes you also see SFG, because that's commonly done where you need the difference between the two, and it saves just a little algebra. But anyway, so you could write H of F plus the quality times HFG, this value right here in the middle of the table. Okay, so I'm running out of room. When you make that calculation, you find that the enthalpy is 2028.8 kilojoules per kilogram, and box it, and there you go. So using quality in the tables. Okay, let's continue on. So now still water, all these parts are with water. We have a pressure of 2 megapascal, or 20 bar. And we have a given specific volume. This time it's not 0.0595, it's 0.1595. So it's a different value of specific volume, and we're asked to calculate the enthalpy H. Well, come down here, and again we compare. Is our V in between? And you find that the V in this case is greater than V sub G, is greater than the specific volume of saturated vapor. Hence, it's not two-phase, it is superheated. We have to go to the table A5, not A5, A4. Go to the table A4 for superheated water vapor data. So, superheated water vapor data, table A4. We look for our pressure block of 2 megapascal, which is 20 bar, and we're looking for a specific volume. Now, it's built such that temperature is the primary input. It gets a little awkward, but you can still do it where you're coming in with specific volume is your second variable. So you're in the right pressure block of 2 megapascal, but you're needing to interpolate with respect to, or look it up with respect to, specific volume. Luckily, this is just all monotonically increasing. That's just nice. So we look for 0.1595, and it looks like it falls right in here, 0.1595, in between those two values. So what I do is I construct a little mini table. Maybe I even put temperature and say I'm grabbing off the line of 400 and I'm grabbing off the line of 440, and I have the specific volume at 400, 0.1512, and the specific volume at 440, 0.1611, and I'm looking for enthalpy. So I skip the U and the S column, and I just put my enthalpy values. And my enthalpy at 400 is 3247.6, and then 3335.5. So these values right there. All right. So I like to think about it this way. I'm coming in with this value, 0.1595. I double check. Is it in between these two values? Yes, it is. That's good. And then I can interpolate to get H, and if I wanted to, I could also interpolate to get temperature. I don't need to, but I could. And so I'll do it in two steps. I'll get that fraction of the distance interpolating, so it'll be 0.1595 minus 0.1512, 0.1611 minus 0.1512, and that fraction comes in at 0.83838, something like that. And now we come and calculate the enthalpy. I'm going to write it like this: the h at 400 plus the fraction times the enthalpy at 440 minus the enthalpy at 400. And so let's write our values. What, 3247.6 plus 0.83838 times 3335.5 minus 3247.6, and then we'll get our final answer of 3321.3 kilojoules per kilogram, and then go ahead and box it. There you go. So check. Let's do our last one. And this one's a little more challenging. We have pressure as our input and enthalpy as our input. Well, you check a little bit, but you're going to end up taking a look at table A3. We come in with the 22.5 bar. We don't have a pressure line of 22.5. We have one below and one above, so it's in between. And all we need to do is check to see about H. Our H values looks pretty high. We come over here and we compare our H of G. We could compare H of F, but we know that it's going to be, this is the key one, it's not going to be less than H of F. It's not between these two values. It's actually above either of these values. So 3275 is our H. It's greater than H of G. So we conclude that we're not two-phase. We conclude that we're superheated. Okay, it's just again looking right here at this value and make that comparison. So we go to our superheated table A4, and we try to find a pressure block of 22.5 bar. We don't find one. We find one at 20 bar and one at 30 bar. So we're in between. We're at 22.5 bar. Okay. And we're interested in that enthalpy of 3275. Well, you kind of look down this enthalpy column and you're looking for where does 3275 fall between? Well, doesn't it fall right in here on this pressure block? And then how about the 3275? Does it fall right in here? Well, this one's nice. It's easy. So it falls in between the 440 and the 400 temperature lines on both of these. So what we have to do is what we call a double interpolation. Double interpolation. It's not that hard conceptually, but we need to interpolate with respect to pressure, as well as you can think of it as enthalpy to find specific volume, or temperature. It doesn't, either perspective. So what I would do is I would construct a table, and I'm going to need a little more room. Let me scoot down and do that. All right. So I construct a table where I grab off at the pressure of the 2 megapascal both my specific volume and enthalpies at the line of 400 and 440. So I'll just repeat those values. So it's a 0.1512 right here, and then 0.1611 from right there, and then our H value is 3247.6, and then 3335.5, just this value and that value. Okay, do the same. Well, let's finish out, do one interpolation on this side. So we come in with our H value, which is 3275. I would do it in two steps. I would get that fraction with respect to H. When you get that fraction with respect to H, it's 31 0.1718, you know, so 0.311718 of the way from here to there, the value at 400 to the value at 440. And then I would use that to interpolate to find V. Okay, so when I find V, it comes in at 0.154286. Now that we did that interpolation, we do it similarly on this side for V and H. And so our V here is 0.0994 from right here. And then it's 0.1062 right there. And our H value is 3230.9 and 3321.5, these two. Okay, we're coming in with the value of 3275. I do that fraction for the interpolation with respect to enthalpy. In this case, it's 0.10271. I use that fraction and I calculate that specific volume at the pressure and enthalpy. So this comes in at 0.10271. So we had to do it twice, but we only did it with respect to enthalpy. Now that once we've interpolated with respect to enthalpy, we want to interpolate with respect to pressure. And so our fraction with respect to pressure is going to be, well, what pressure do we need it at? We need it at the 2.25 megapascal. Our lower pressure block on the left side is at 2 megapascal, and our higher pressure block on the right side is at 3 megapascal. And so our fraction of interpolation with respect to pressure comes in 0.25, 25% of the way. Hence, I'm just going to finish this out right here, that we're looking for our specific volume. It'll be the lower value, 0.154286 plus that fraction, 0.25, times the 0.10271 minus the 0.154286. All right, so this is interpolating with respect to pressure, where before we interpolated up here with respect to enthalpy. All right, so our specific volume comes in at 0.141, I'm going to round it off to 4 meter cubed per kilogram and box it. Yes, it is a double linear interpolation. It isn't that accurate, but it's accurate enough. And yes, we have to do that every now and then in our steam tables. So with that, I thank you for your attention. Let me just scroll back up. Yeah, that's the right answer right there.